In this lesson, we're just going to do a review of graphing rational equations. All right, so let's talk about end behavior asymptotes. And end behavior asymptotes are basically like your horizontal asymptotes or your oblique asymptote. The relationship between the degrees of the numerator and denominator determine the end behavior asymptotes. If the degree of the numerator is larger than the degree of the denominator, you're not going to have a horizontal asymptote. That means that your numerator is growing faster than the denominator. Note that you get in OA if degree of numerator is 1 more than degree of denominator. And we also have to remember and no common factor. So if you have a common factor, that would cause a whole, right? So so if your degree of the numerator is greater than the degree of the denominator, you're either going to have an oblique asymptote if the degree of the numerator is 1 more than the degree of the denominator and there's no common factor. But if it's like 2 or 3 degrees bigger than the degree of the denominator, then you're not going to have a horizontal asymptote. Okay? And you're not going to have an oblique asymptote either. If the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is basically your leading coefficient over your leading coefficient. So if they have equal degrees, it's going to be leading coefficient over your leading coefficient. That's where your horizontal asymptote is going to be. The degree of the numerator is less than the degree of the denominator. So that means your denominator is growing faster, then you have a horizontal asymptote at y is equal to 0. Remember that horizontal asymptotes can be crossed, and you can check by using Desmos if you want. You can graph this function. You'll see that the horizontal asymptote does get crossed. Steps for graphing rational functions. So the first thing that you're going to want to do is you're going to want to factor. If you cancel common factors, use the reduced function for the remaining step and make note of the wholes, right? If you have a common factor of the numerator and denominator, then you're going to have a whole. Determine the existence of vertical asymptotes and their order. So like, is it going to be, opposite extreme or same extreme behavior, horizontal and oblique asymptotes, and sometimes they can be crossed. Zeros and their orders. So is it going to pass linearly through a 0? Is it going to be quadratically through a 0? So on and so forth. And the y-intercept if it exists. So we're going to sketch it. We're going to use dashed lines for asymptotes. We're going to plot the zeros and y-intercept. And then we're going to try and sketch the graph. We could start from the left of the grid, or we could look at points to see how we do this. Again, same thing with the vertical asymptotes here. We're looking at either opposite extreme behavior or same extreme behavior. If the order is odd, we're going opposite extreme. If the order is even, that's same extreme. And then we've talked about this before, right? At the zeros, determine the order, the factor causing the 0, and is it going to pass through linearly, quadratically, cubically, so on and so forth. Okay, let's just get to it. Here we have what looks like a pretty complicated graph, but it's actually not that bad. And the first place that I usually start with is the vertical asymptotes because they're pretty easy to see right away. So the first vertical asymptote I'm going to look at is this one over here. So x is equal to -1, and this is going to have opposite extreme behavior. The next vertical asymptote I'm going to look at is x is equal to 5, and this is going to have same extreme behavior because the order of that one is 2. All right, it wouldn't hurt to go ahead and graph those, so I'm going to go do that. Okay, vertical asymptotes are now drawn in, and I'm just going to go ahead and label them. X is equal to -1 and x is equal to 5. Okay, so the next thing that I'd like to look at is I'd like to look at the horizontal asymptote. And in this case, it's going to be a little bit more complex, right? So what I might do here is I might want to expand briefly, and I'll tell you what I mean by expand briefly, okay? And look at degrees and leading coefficients. So what do I mean by expand briefly? Well, if I take this 3x and I expand into this, which is squared, then my numerator is going to be something to the effect of 3x cubed plus some other terms, right? That's going to be the highest degree, right? x cubed, and my leading coefficient is 3. Look at the denominator. If I expand this denominator, well, there really is no leading coefficient other than 1, but the degree is going to be also 3. And then there's going to be a bunch of other terms, right? The reason why I'm doing this is because as x goes towards infinity, these other terms kind of become irrelevant, right? Because I'm looking at my end behavior. And so I'll write that as x goes to plus or minus infinity, then my y is effectively going towards 3x cubed all over x cubed, right? And so effectively I end up with just 3. And that relates back to what we said. The degree of the numerator is 3. The degree of the denominator is 3. So the degree of the numerator was equal to the degree of the denominator, and so effectively we're just looking at leading coefficient over leading coefficient. Well, the leading coefficient is 3, the leading coefficient here is 1, so my horizontal asymptote is y is equal to 3. So I'll go ahead and I'll plot that. Okay, so it's plotted and labeled. And now what I should do is I'm going to look at x-intercepts. Okay, so x-intercepts. So I look in the numerator and I look at the various factors, x plus 3. So that means x is equal to -3, and it's going to behave quadratically or parabolically around -3. And this one's going to be 4 over 3. The other one's going to be 4 over 3. And it's going to behave linearly through that one. So let's plot that right there. Okay, so that's going to be -3, 0. And that's where I'm going to have my quadratic behavior. And then I've got 4 over 3, which is 1 1/3 right here. Okay, and it's going to behave linearly through that. Last thing I want to look at is I want to look at my y-intercept. My y-intercept is done by setting x is equal to 0. So if I look at this expression and I set as x is equal to 0, well then I'm going to get 3 squared, which is 9, and then I'm going to get 9 times -4, so I'm going to get -36 in the numerator. In the denominator I'm going to get 1, and then -5 squared is 25, so 25. So -36 over 25, so if I was to actually look at that as a decimal, that's approximately equal to -1.44. So somewhere around here. So 0, -36 over 25. All right. Let's just start with the x-intercept and the y-intercept. I know it's got to pass through this linearly, right? So it's got to pass through this linearly, and it's got to go through the y-intercept, okay? And I know it can't curve back around because there's no x-intercept over here. So I know it's got to do something like this. It's got to pass through linearly here, and it's got to go down this way. All right. And then what's going to happen here is it's going to go up towards infinity here. I know it's not going to go back down towards -infinity because it can't cross the x-axis again. So the only direction it can really go is back up that way. Okay. Now I look at my vertical asymptote here at x is equal to 5, and I have same extreme behavior, so it's not going to change sign across that vertical asymptote. So that means it's got to do something like this. And then come down here. Okay. Now whether or not it crosses this horizontal asymptote here, we're not going to worry about for now. I just want you to know about the end behavior and about this same behavior here. So whether it goes down, comes back up, that sort of thing, you don't have to worry about that for now. We're going to find more effective ways of determining that in calculus. What we'll do right here is we've got our same end behavior and we've got our end behavior over here, right? So same extreme behavior here and end behavior there. That looks good. Around the -1, we had opposite extreme behavior. So if this was going down towards -infinity, that means that this one's got to go up, right? So this one's got to be coming up this way. And then I also look at this x-intercept here, and I see that it has quadratic behavior. So that means I've got to go all the way down, okay? And I am crossing my horizontal asymptote because I have to, that wasn't a great one. Let me try this again. It's got to cross, and then it's got to bounce off quadratically. It's not wanting me to do it as a curve, so I'll just do it myself. Here we go. And then it's got to come down, something like that. Okay. Again, whether or not it goes above and then comes down, you don't really need to worry about that for now. But what you definitely need to worry about is the quadratic behavior around this 0, and the fact that if this is going towards negative infinity, so let me just use my mouse here. If this is going towards negative infinity, then this one had to be positive infinity because it had opposite extreme behavior. All right, and there is the shape of this kind of complex rational function here, which, yeah, we're just basically decoding using our behavior around the vertical asymptotes, our horizontal asymptote, the x-intercepts, the behavior around those x-intercepts, and the y-intercept. Okay. All right, yeah, that's pretty much it for now. Thanks again for watching, and good luck with the homework.